I'd like to kick off this presentation with this meme I found somewhere on the internet, and it is because it really captures the premise of this talk, which is unlearning the stuff that you got wrong. Because sometimes you had these pieces of information and you really need to connect them to form knowledge, and you see the conspiracy theory just picks the information it needs and leaves out all the rest. However, sometimes you just think that you were right about something because it made sense, it connected well with everything else, and then you get a new piece of information and everything falls apart. So the first time I had this is when I was doing the model thinking course on Coursera, and there was a topic about overbooking flights. So now probably everybody knows about overbooking flights after the United Airlines thing. However, the math behind it is really amazing, because how many people don't get to the plane follows a standard distribution. So if you have 200 tickets to sell, and usually on average 8 people doesn't show up and the mean is 2, you can safely overbook average minus 2 means of places, and you have 95% chance that you will be all right. And in all those 5% where actually people show up and there's more people than places in the plane, you can simply give them a refund, a free flight, nice hotel, and you will be still ahead in terms of money. So I wanted to show that example because this was something that I assumed about flights. If I was going to make a flight booking application, the first constraint on my database would be that there can't be more bookings than seats in the plane. However, the financial systems are riddled with so little misconceptions. So this talk will be split in 2 parts. The first part is about properties of business domain that affect distributed systems, and my domain is the financial systems. And the second part is why would we choose Elixir for non-distributed system, because we ended up with a really small system and basically it's a crude application. So let's kick off with a little bit of theory, and I want to compare ACID and base systems. So ACID stands for atomicity, consistency, isolation, and durability, and this is something that we usually associate with SQL databases. So there are 2 important things for this talk in the definition. The first one is consistency in ACID, and it means that any transaction will bring the database from one valid state to another. So consistency in ACID is about this set of rules that the data follows, and it can't be broken. In case you want to insert to the database something that doesn't follow these rules, you will get an error. The other part of the definition that is important here is isolation. And there are 2 definitions of isolations in ACID. First one says that concurrent execution of transactions result in a system state that would be obtained if transactions were executed sequentially. And this is a really hard statement, because it means that for all transactions, you need to preserve the order. The second definition says that transaction will behave as if it is the only operation being performed upon the database, and this basically means that we don't have to worry about other stuff that is in the database. So in ACID systems, if we have distributed database that is ACID, it needs to preserve the order of transactions. We have, for example, 2 writes. One of them hits the first node, second one hits the other node. And if there is a net split between those 2 shards of the database, you can't run the transaction. You can't write anything, because those shards need to communicate and need to specify which transaction was first. They need to serialize the data. And this gets us to the CAP theorem, which says that in distributed systems, and especially in databases, there are 3 properties. There is consistency, availability, and partition tolerance. And given that partition tolerance is a fact of life, it just happens even in local networks, we can only trade consistency for availability. But the consistency in CAP theorem has different definition than consistency in ACID. Consistency in CAP says that every read receives the most recent write or an error. So there's a second definition of consistency. And to make matters more complicated, there's third definition of consistency from consistency models. And in consistency models, you will say that it is a set of rules that must be followed by transactions. And this is a little bit vague, so it works better on an example. There are a couple of models of consistency. The first one is strong consistency, and it corresponds to this definition from CAP theorem. It says you either get a most recent write or an error. However, there are other kinds. For example, weak consistency means that if some conditions are met, then you will get a system that is consistent. This is again a little vague, so one subset of weak consistency is eventual consistency, where this rule is that if enough time passes, you will get a system in a consistent state. The other subset is causal consistency. So if the parts are related, then you will get the most recent write, and in all other cases, you will get the eventual consistency. And again, a subset of that is read your write consistency. So if you have an agent writing to the database, if that agent wrote something to the database, it will get the most recent write. And this is easy to implement if, for example, for each client, you always hit the same shard. So we can see, again, an example where we have this time similar database that it has 2 shards, and we give it 2 writes, and they immediately succeed. So even in case of net split, the first part is written to the first node, the second part is written to the second node, and when the connectivity between them is, again, online, they just share the data, but they cannot agree, and they usually don't, about the order of transactions. And that's fine for many, many cases. And those systems are called basically available, soft state, and eventually consistent. So our financial systems that we are working on, ACID or base? So at first, I thought they were ACID, and this is because one of the first assignments in operating system class was about mutexes, and the example was a little bit like this. We want to transfer money from Alice's account to Bob's account. So we firstly check if Alice has enough money to transfer the amount. Then we calculate what will be the new amount that Alice will have on her account. Then we calculate the new amount that Bob will have on his account. Then we assign the actual computation to the Alice's account. But in multi-threaded system, we can be preempted at any time. So let's say our execution stopped in here, and someone just sent Bob $1 million. So Bob is now really rich and really happy, but then the execution comes back to the first thread, and Bob has the value that was computed earlier assigned. So this means that Bob is now a really unhappy person. So in the end, it's a really cool example of where you should introduce mutex in your system, but no one in their right mind does this stuff in actual financial systems. What we usually do is we create an immutable set of transactions which specify an amount and from who to who the money is transferred. And the most popular accounting scheme is double accounting. So you copy this event to both Alice's and Bob's account. And in case of Alice, it will subtract money from the balance. In case of Bob, it will add this money. So this is totally immutable, no mutexes needed. And the problem with financial systems is that we can't say if they're ACID or base by principle, because some parts of financial systems can be ACID and some of them can be base. So for example, in case of PayPass transactions, some banks do it in this way. If you pay amount that is small enough, like smaller than 10 euros. You just swipe your card, and the transaction is registered immediately. So the request doesn't even come to your bank. It simply registers it for later. So if you, for example, check your statement online, you won't see this transaction at all. It's nowhere to be seen. And after a couple of hours or even the next day, everything gets synchronized. And it works a little bit like with overbooking, because that means that you can get a negative amount on your account, because those transactions are just summed up later. And in such a situation, someone phones you from the bank saying that you need to immediately put something on your account, otherwise like really bad stuff happens. Of course, that's not the case. Nothing bad happens. It's their fault. So they can't do much to you about it. So this works a little bit like with overbooking. We trade that the transactions are really fast for the possibility that in some edge cases things might go wrong. And I remember I was giving a talk about Elixir and Elm programming languages, and I was explaining that Elixir is really great for those systems that trade availability for consistency. So it's really cool for those base systems. And Elm, which is a front-end language, is really cool for what browser does. And browser does it usually in one thread, and you can serialize everything, and you get a language that is much less complex than Elixir, but you can't do the distributed stuff easily. It's not meant for that. So after the presentation, I got a question from audience asking, okay, so what do you do at Club Collect? And I was like, yeah, we're doing a financial system. Oh, so you can do that in Elixir. And I was a little bit baffled, but now I understand that it is because Elixir is marketed as something that is used for distributed systems, but actually you can totally ignore all those fancy stuff that Elixir provides you and use it with all the boring, crude applications, and it will work just fine or even better than popular object-oriented solutions. So now you know that we're dealing with money, and in our case, we're using direct debits, which are processed offline, so the order doesn't matter. And the question for you is, what do you think, what database solution did we use in our system that handles money? Like, what database would you prefer? So at the end, we just used Postgres. Why? Because in case where we can decide what solution we want to use, ACID or base, we would always go with a solution that is more constraining, because it's easier to eventually migrate for something that has less constraints than the other way around. Another thing that is baffling for Elixir and financial systems is let it crash philosophy, because people often think that let it crash means that we can lose the data or something bad happens. And that's totally not the case. It's almost the other way around. So let it crash philosophy means that we sprinkle our code base with this equal operator, which isn't assignment, it's pattern matching. It just checks if whatever is returned on the right matches whatever is on the left. So this means that in case the file write was successful, the execution will continue normally, but otherwise the process will crash. It doesn't mean that we handle all errors somewhere else. So if we have a business logic that requires handling the error in file write, we can totally do it in case statement, but we don't handle the errors that we didn't think about. So it's more like a happy case programming. We just restart the process and try again. And this is something that is surprisingly useful. For example, we're using Heroku for our infrastructure, and in Heroku documentation you can read that dynos are restarted at least once per day to help maintain the health of application running on Heroku. And this basically means that there were applications with memory leaks, and it's just better to restart the application once, roughly 24 hours, than to simply keep it running and have it more and more memory. Also, any changes to the local file system will be deleted. So if our application crashed because it did something really stupid and it can't recover from it, it will start with a clean state. So this is almost the same philosophy. So again, question for audience. Would you fly a plane that was written in let it crash philosophy in mind? Because I would. The only language that I know that supports let it crash philosophy is Erlang, and by transition Elixir. The problem is that let it crash is something that we associate with blue screen of death, like everything crashing, our entire application going down. That is something that we usually associate with crashing. But actually, the philosophy was used even before Erlang and Elixir. So in Apollo 11, there was a primary guidance, navigation, and control system, and they had a shared CPU. And this CPU wasn't very powerful, so each application that was using it had a bound of how many cycles can it use. So for example, for moon landing, they used 80% of CPU cycles. For querying the system for any data, so for example, if crew wanted to check something, it was something about 9%. And the problem was that there was one faulty hardware that used constantly 13% of CPU cycles during the Apollo 11 mission. So during the moon landing, someone from the crew asked the computer about something, and the query they did crash because it ran out of CPU, but it had also the lowest priority. So moon landing had, of course, higher priority than whatever crew wanted at that time. And this is the embodiment of let it crash philosophy. We contain the error so it doesn't spread and it doesn't crash entire rocket. But it also forces us to think upfront about the design. So if anything in our application can crash and can be restarted at any point in time, how do we solve the client-server communication? So for example, I'm currently working on the server part that accepts transactions and then sends them to the bank in whatever format bank needs at this time. So it works a little bit like this. When we get a transaction, we do some processing to check if the data is valid and whatnot. Then we do the DB access, and it can also fail because we use Postgres and the constraints might not be met. And then we do some more processing, and then we send the response to the client. And the client usually firstly creates the transaction, saves it somewhere, then sends it to us, and then after getting the response, it also saves it. So it's a synchronous thing. And this is because any part of this computation can fail. So for example, the network can fail and we don't get the response. Or the first processing on the server can fail. And in that case, we won't save anything to database. But if the second part of processing failed, we have something in the database. So how do we make sure that both client and server are on the same page? And there's a really great example of two systems trying to set on the same state. It's called two general problem. And the story goes like this. There are two generals on two sides of a city they want to attack. So their armies are big enough so that if they attack both at the same time, they can win. But if one of them attacks, then they'll probably fail and get slaughtered. The problem is that they want to communicate this time, and they need to send a messenger to the second general through that valley with that city, so this messenger can get picked off. And this is the perfect metaphor of network. So General A sends a messenger to the second general saying, okay, let's attack tomorrow at noon. Can they attack? no, they can't, because even though the second general knows the date, the first one doesn't know if the second one got it. So they send a messenger back saying, yes, okay, we will attack at noon. Now, if both messengers got there, can they attack? No, they still can't, because the first general now knows that the second general knows the date, but he also knows that the second general doesn't know if the confirmation got in. So even with infinite amount of messengers getting back and forth, you can't simply agree on a date. And there are big class of complex algorithms to set a shared state. However, in client-server architecture, we don't need that. Client-server architecture is much simpler than that, because server usually doesn't have to know if client got the response. It's client responsibility to wait for the response, and in case it didn't get there, just retry. However, retrying is another problem in itself. If we only set a transaction with amount, from, and to, if we send it twice, is it the same transaction, or are there two different transactions? So how we usually solve this problem is that we use idempotent calls with client-side generated UUIDs. So every time client wants to send a request, it generates a UUID, and this way we know that this is this particular request. That's why the client saves the request that wants to send to us before actually sending it to the server. And also, because we use HTTP interface, we use put methods for that. And this means that if the server produced the response and somehow it didn't get to the client, then the HTTP layer can cache that for us, because put is idempotent. So now, as I'm talking about it, you can get a picture of what we're working on. And this slide shows how people usually see Elixir, like great for distributed systems, great for complex stateful communication with channels, for example, perfect with base databases. And how we use Elixir is the exact opposite. So we have a single node service, we have a client server without state, and we have AcidDB, Postgres. So why the heck do we use Elixir for our system? And it is because functional programming can make it more easy to reason about our problem domain. So one of the things is that it helps us keep side effects in check. For example, if we do testing in imperative languages, it usually goes like this. We set up some state, we then run the tested code, and we check the new state. In functional programming, it is very similar. We set up a data structure, then we run our tested code, and then we check the data structure. So from the programmer's point of view, it's basically the same. But if we want to run those tests, we can do it in parallel. And this is an important win for us, because our test case can run in like 3 seconds or less. What's more, Elixir with its pipe operator encourages a certain way of programming where we firstly gather data and we have all the impure operations in one function that gathers the data. For example, reads the HTTP request from socket or reads data from the database. Then we make a series of transformations that are pure and have no side effects, and then we return the data. So we again push something through the socket or insert it to the database. And this allows us for very easy testing. So we firstly set up the data structure. The data structure in Phoenix that is used for testing is called con. Con has everything that we need to know about the HTTP request, like its body, its query parameters, and we also set the response in this data structure. So we firstly build that, and we have a function that does that for us. And then we invoke our route to some path, and this basically tests all the code that we have written, our router, our controller, everything. And then at the end, we check the data structure if everything is correct. So for example, we check the con data structure if the HTML response was actually 200 as we expected. And the only quirk here is that the first con and the second con are two totally different data structures, because Elixir is immutable, and it might be a little bit confusing that you can rebind the name of a variable. It's not actually rebinding. The problem with this approach is that sometimes in those transformations that we want to keep pure, we also really want to do something impure, like insert something to the database. And Ecto, which is the database library for Elixir, helps us with it by introducing Ecto multi. So let's say we have a transformation that doesn't touch the data at all. It simply inserts some subset of the data to the database if some condition is met. So this if is our business logic. What we can do now is introduce the multi that will carry the operations for the database throughout our pipe chain. So let's say that the first multi we send doesn't contain any database operations. We do exactly the same as before. If some condition is met, insert something to the database, but instead of touching the database directly, we use multi-insert and then return the new multi alongside the data that was unmodified. So in the tests, it looks then like this. We again start with a pure data structure, simple data structure. Then we call our function, and we check that the data is unmodified and that the Ecto multi has this transaction that we want to perform on the database later. So we can pass this multi around, keeping our computation pure, and then at the end have all the database transactions run at the same place. That means that we can easily write unit tests that don't touch the database and are really, really fast. And then we can write one big test that actually checks if the database works correctly. The other problem we can get is the opposite. So if we want to really read something from the database in this pure part. So in that case, for example, we again have some business logic, and depending on what the database returns, we want to either add something to the processed data or just return it unmodified. So in that case, we can use default arguments. So what I did there is I introduced another argument, which is the lowercase repo. The // means the default will be capital R repo. So if you call this function with only one argument, it will behave exactly the same as the one from previous slide. However, you can define a fake repo module that will have the same interface as our database. And then when you test this stuff, you can simply pass this fake repo module and again save yourself the hassle of going all the way to the database. There are also other benefits, like for example, Elixir and other functional programming languages are very explicit. And there are many questions on mailing lists, on forums, on Stack Overflow about how do you add callbacks to some stuff. How do you, for example, make sure that after you write something to database, another piece of code gets invoked? And the answer is you don't. You simply don't, because it makes for a tangled design, and you simply can't do that in Elixir. If you want to do such stuff, you just create a function that firstly does the write, and then secondly does whatever you want to do in your callback, and then use that function. So it makes the code much more readable and much more sane. The other thing is really great performance. For example, comparing to Ruby. I think in 2 slots, Ben Marks will be talking about his experience at Bleacher Report. they wrote that they had 150 servers running Ruby code, and after they switched to Elixir, they have now 5, and they're probably over-provisioned. So this is something that I would like to say about our case, but we didn't get the measurement, and we're still in the process of rewriting the Ruby monolith to Elixir code. And I hope that at some point I can give similar data to this. However, this is probably one of the things that helps us keep our system non-distributed. We run everything on one node, and this is because Elixir is fast enough to handle it on one node. The other thing is that Elixir is very focused on getting your design right. So many frameworks would like you to put things that are meaningful for framework and not for your application in different folders. So if you have a separate controllers directory or separate models directory or separate views directory where you have many unrelated views, that's something that is a little bit fishy. And if you're following domain-driven design, then you'd like to put your code that makes use of other modules close to each other in the same directory. And Phoenix currently really encourages that. Also, if you have a piece of functionality that is really separated to the point that it uses different storage solution than the rest of your application, you can put it in the Elixir application and then use umbrella applications. And this is something that resembles microservices because you can put many pieces of functionality in one big chunk, so it gives you the same benefits of isolation. However, it's still one Elixir system, which means that it saves you the hassle of dealing with HTTP requests, network, and so on. Of course, like with everything, there are some trade-offs. So, for example, rapid evolution can be a disadvantage. And we've heard during the keynote that the evolution slowed down currently, so this shouldn't be a problem anymore. However, there were a couple of examples where we needed to refactor all of our models because Ecto changed the API. However, it was really painless. The changes were mostly mechanic, so we did a query search and replace with our editors, and if the tests passed, we were pretty confident that everything worked as expected. The other problem is compilation time, and there was another great talk just before about how compilation in Elixir works, and Elixir has this tree of dependencies. So if one module A depends on the module B, if you change module B, module A also needs to be recompiled. And there are modules in your project that are in the bottom of this hierarchy and trigger recompilation of entire project. And this is, for example, the case with config files. So every time you change a variable in config, it means that you will recompile everything. And that's not a pretty big deal because usually most of the modules don't have such big dependencies, and we don't edit the configuration very often, but still it can be something that maybe can be somehow improved. The other thing is that type system is optional, and I point it as a problem because other languages, like for example Haskell, where the type system is strict, give more safety net, and it is very common in Elixir to pass wrong data structure or a little bit wrong argument. And of course, we usually catch such stuff in tests, but it would be great to have to enforce type system in project. So in Elixir, there is a dialyzer, and you can use that. That's why I say it's optional. But it works best if all the libraries that you're using also use dialyzer. And not all libraries that Phoenix uses use dialyzer, and that means that in the end, it's quite hard to use it, and we simply opted out. And another thing is libraries. So there are more and more libraries for Elixir. That's why I put a question mark here. I never had a problem with finding a library that I need. However, it's not as rich as languages that are there 10, 15, or 20 years. Okay, to sum up, this talk was a success story of Elixir, and I think that we need more success stories for small applications, more crude applications where we don't have this fancy distributed stuff, because Elixir could really spread in the environment where we do the simple design. And I think we're not marketing Elixir enough for those kind of systems. The other thing is, don't assume financial systems are ACID, because it really depends on the problem domain, and there are cases inside cases where you should switch between ACID and base design. And the third thing is that Elixir can solve really hard problems, like in concurrency, in stateful systems, but it can also help something solve the simple ones. And that's all. Thank you very much.
Well, thanks a lot. That was great. Does anyone have any questions? I can come around with the mic if you put your hand up. There we go.
Hello.
Hello.
Great talk, by the way. Thank you.
Thank you.
Question about working with money, specifically working with rounding of pennies. Say you're dealing with taxes, and maybe your taxes are 6.5% or something. Just wondering if you have any short lessons learned working with rounding numbers.
Yeah, so for storage, we usually try to store everything as integers, and if we don't have to store something like ratios between currencies, it's usually enough, because we can just multiply the number by 100. And for all the other cases, we use the decimal library, where we can specify exactly how do we do the rounding, and how many decimal places do we keep in the answer. And at the end, we only use this library in the front end, so to show the data, but we don't store decimals anywhere, and that simplifies things greatly in our case.
Does anyone else have a question?
Okay, thanks for your talk. I wanted to ask you about specific about financial systems. How do you handle cases where you have a process or an application that is handling a transaction, and then the process or application crash, and you need to recover the states to maybe retry the transaction, or what you actually do? What kind of behavioral heuristics do you implement?
So this is a little bit connected to the slide about client-server architecture. So I'll rewind to that. Here, so in case the application crashed during the processing on the server side, and we know, the client knows that it sent the transaction okay, and it didn't get the response, the client is responsible for retrying that transaction. So that's usually the case. If something goes wrong, someone knows that it should get the response. So we push as much responsibility as we can to the client, because only the client can know if everything was processed as intended. So even if something crashes on the client side, so for example, sending fails because of network errors, we always store everything that we want to do somewhere. It might be in logs, it might be in the database. So if we want to create a transaction, the client firstly saves it, then tries to send it. And from that point, if anything fails, then we have a transaction that is stored somewhere but doesn't have the corresponding response. So that's the way we handle errors, and that's the way we leverage on the let it crash philosophy.
So we have about a minute left if someone wants to squeeze in one more question. Anyone else? Going once, going twice. All right, well, that's a wrap. Thanks so much for the presentation. It was really fantastic.